Hello everyone, this is Vasant, a nine-pointer at IIT Bombay from the Department of Civil Engineering. Today's topic is about normal strain. We already know that load has two consequences. One is internal forces and other is deformations. To understand deformations, we need to know about normal stress and normal strain. We completed internal forces and normal stress in previous lectures. So today's lecture is about normal strain. So if you take a bar which is subjected to a tensile axial load, so it will, what this tensile load will do. See, if you consider any two particles, it will try to stretch these particles away from each other, right? So that is what we call as deformations. But there is a bond between these two particles, so because of which there will be internal resistive forces developed. So internal resistive forces are developed because to resist these deformations, right? So deformations are first, then internal forces. Means so we define one parameter called as strain, which is denoted by epsilon. Here it is normal strain because it is normal to the cross section. So it is defined as change in length divided by original length. We already said that due to this tensile load, there will be deformations. Deformations means change in shape or size. In this case, there will be change in size, right? So there will be change in length. So suppose final length is L plus delta, initial length is L, so divided by original length L. So strain epsilon is given by delta by L, right? So this will be positive value because it is tensile load. If it is compressive, then it will the length will decrease. So the change in length will be negative. So the strain will be negative. So normal strain will be positive for tensile load. It will be negative for compressive load, right? So what is the need for this parameter? So we already have change in length. Then why we need to define a parameter called strain, which is given by change in length divided by original length. See, if you observe, it will give the deformation per unit length. Means suppose this is 1 unit length, then it will give deformation of this 1 unit length, right? So this will give better, because of this it is a better parameter. How? See, if you consider 1 unit blocks, these all are 1 unit blocks. So you applied a tensile load P. So here there are 5 1 unit blocks, so its length will be 5, right? So let us take 7 units. So here 7 units of 1 unit blocks, and let us apply P. See this total length, this is 5, this is 7 units, right? See, in second case the change in length will be more, right? In first case the change in length will be less. But if it is elongated by 5 units, suppose it is elongated by 5 units, then it will elongate by 7 units for same load, because load is same. So if you consider per unit length, then both will elongate by 1 unit, right? So each link will elongate by same, each will elongate in same amount. This means the amount of dangerousness, means the probability of failure is same in both cases. But if you only consider change in length, you may confuse that the first one is in danger zone, more danger zone than compared to the second one, right? But here both are in equally danger, right? So this is the reason why strain is a best parameter compared to change in length. So before moving into deformations, we need to understand Hooke's law of linear elasticity. See, we have normal stress and normal strain. Normal stress is the representation of internal forces. Normal strain is the representation of deformations. We already said in earlier lecture that we can relate these two things. So we can relate normal stress and normal strain. So in particular range of normal stress, the normal stress sigma will be directly proportional to the normal strain epsilon. If you see here, it is a straight line. So normal stress will be perpendicular to the normal strain. So sigma is equals to E into epsilon in OB region, right? So this is Hooke's law of linear elasticity. This E is constant, right? Here, this is material property. It is known as modulus of elasticity. This is one of elastic properties which we said in classification of materials lecture. Right. So in deformations, we only consider this region for solving how much the member will deform. Why? Because see the value of E, will be very high for the materials which we use in civil engineering construction. So then the angle theta, this angle theta in this region will be given by tan theta, will be given by sigma divided by epsilon, that is E, right? So theta is given by tan inverse of E. So as E value is very high, E is very high, so theta will be almost nearer to 90. Means this angle alpha is very less. So the deformation, see the deformation term is this, right? This is the epsilon. So this will say the change in length portion, right? This represents change in length. So if the m, y, this is y equals to mx, right? So m is slope, slope is e. So slope is more, means the straight line is towards the y-axis, right? So for high values of stress, the epsilon is very less, means the deformations will be very less. Means in OB region, deformations very less, right? So and these are elastic. Elastic means if you remove the load, then they will regain its shape and size. And this linearly elastic means it will regain its shape and size in the same direction. Means see the elongation is in this direction. So if you remove the load, the recovery will also be in the same straight line, right? So we consider only this part to find out the deformations in the member, because whatever structures are designed for civil engineering are designed for these deformations only. That is the reason why we consider only elastic region wala deformation part. So this is about Hooke's law. Hooke's law means sigma is equals to capital E into small epsilon. Sigma is normal stress, E is modulus of elasticity, epsilon is normal strain. So about modulus of elasticity, I said earlier modulus of elasticity is a material property, right? So see sigma is equals to E into epsilon, right? Sigma by epsilon is equals to E. If you increase E, let us write like this. Sigma by E is equals to epsilon. If you increase E, what will happen? Epsilon will decrease, right? Epsilon means change in length will decrease. Length will be same. Initial length, original length will be same. But so epsilon is decreasing, means change in length will decrease. This means change in length is less, right? It means if modulus of elasticity is more, then the deformation is less. So that is the reason we said that elastic modulus of elasticity represents the resistance of the material. Resistance of the material to linear deformations. In similar lines, it is stiffness of the material. Stiffness means same resistance to deformation. Okay. We have one more term, strength. Strength means maximum stress a member can bear without failure. So this is strength. We generally deal with strength of the material. This is the reason why we also call this chapter strength of material. So this is about modulus of elasticity. Let us move ahead. So now we came with the deformations. See, we completed normal stress and normal strain. So now we can do with deformations. So if you consider a simple member and it is subjected to tensile load P. One more thing. So this is known as stress strain diagram. This is stress strain diagram of a member in tensile load. So we deal about these all portions in future lectures. For now, you only remember that whatever deformations we deal with, that is only in the region of Hooke's law, right? So this is the simple member subjected to tensile load. See, sigma is equals to E into epsilon, right? We already said that we assume the stress distribution will be uniform. So we can write sigma is equals to P by A if this cross section is A. Here cross section is also constant, right? So P by A is equals to E into what is change in length delta divided by L. So delta is equals to P L by EA. But this is not always the case, because in some cases area will change. In some cases value of E can change along the length, because it is not always true that it is homogeneous and isotropic material. And in some cases the load at every section will change. So we need to sum the deformations of each small particles. Then you will get whole deformations in any case, right? So suppose let us consider dx. So then what you can write, d delta, this is deformation of this small dx element, will be T internal force. If you take that free body diagram of this dx, will be subjected to some P internal that can be found out by equilibrium. So d delta will be is equals to P internal into length is dx divided by E, and area of this is A. So area A. So to get whole deformation, we will integrate. So delta is equals to integral P internal dx divided by EA. Right? So this is the formula for axial deformations due to axial load. So we will solve different types of problems of this axial load in future lecture. So with this we end for today. In next lecture we are going to solve different kinds of problems on axial loading. Until then, take care. Bye bye from 9pointer.